I do have all the videos out there and everything, but if I cancel class, I get in trouble. Which, I mean, I'm not going to do, but it's just like really awkward for me still here with 4 of you in this big room and whatever else. And some of you are doing really well, at least the ones of you showing up here are doing really well, and those that aren't showing up, as a general rule, are not doing very well. So, but who knows what will happen if those people are going to drop or withdraw or what the heck, or take an F, but it's not looking good for a lot of those that aren't showing up. So, that said, I just, before I came in here today, you should have all this beautiful demo stuff, and I was going to give you some pre-spring break demos and everything with liquid nitrogen, and I went to fill up, I did some liquid nitrogen demos yesterday. The tank was full. When I went to put some liquid nitrogen in my containers this morning, the tank was empty. So I don't know if somebody left the valve open or what yesterday, but I don't have any liquid nitrogen stuff to demo to you today. I do have some other demos we can do, but unfortunately the liquid nitrogen demos either aren't going to get seen or they'll have to wait till some other point in the semester. So I apologize for that, but it was going to kind of be my little pre-spring break treat for you. But maybe it'll be like a pre-finals week treat for you, because we do have a little bit of built-in time there at the end. So I do apologize, but honestly, I had some demos set up there for you today. Okay, first question that we had here waiting for you was with reference to the demo we did last week and talking about the density and the molar mass. We did not find that they were equal to each other. We found out that they were directly proportional to each other. And what does it mean if we have a direct proportion? If we double one variable, the other one will double as well. Exactly. Or if we cut one variable by a factor of 10, the other one will get cut by a factor of 10 as well. So that's a direct proportion. Then we have what's called an inverse proportion. Inverse proportion is not with density and molar mass, but if we had something where we have an inverse proportion, that means if we double one variable, the other one will get cut in half. And if we cut one by a factor of 10, that means that the other variable will multiply by a factor of 10. Exactly. So those are the terms that we're going to be using here today. And we'll actually reference them several times throughout the semester. Before we do that, though, I did think of some other demos, like extremely quick, that we can do to take the place of liquid nitrogen ones that we aren't going to be able to do today. So first one that I have here, I have a couple of pop cans, and what I'm going to do is I'm going to heat these pop cans up until they get smoking hot, and then we're going to invert them. You just saw me fill up this beaker of water here, and we're going to watch what happens when I heat these up. And make sure I get some eye protection here. And these I just pulled out of the recycle bin right here. If they are sugar-based sodas like this one is, we can get a little bit of charring from the sugar left behind, but we'll take this pop can here, we'll heat it up till it gets smoking hot. Once it gets smoking hot, we put it in here. We see that not a whole lot interesting happens to it, but it does, once we put it into the water, does seem to draw a little bit of water up inside of here. If we go to the second one here now, this one was an empty one. What I'm going to do with this one, I'm actually going to put a small amount of water into this one, and I'm going to heat this one up till I get smoking hot. Of course, because of the water that's in here, it's going to take, is it going to take longer or less time for it to get smoking hot? A little bit longer, sure. So we heat this one up, And actually for this one to be successful, what I need to do is make sure that the water gets heated long enough so it displaces the air that's inside of here. And so what I like is a can that is basically full of steam, or water in the gaseous phase. And looks like we got it smoking hot here. I'll go ahead and invert it into the bucket, and we'll see how the thing winds up collapsing. And just to show you that this isn't a magic can or anything over here, I had a little bit of water that's in here now. Oh, yeah, well, it's charred. Must be a little bit of sugar left behind. So I'll take that little bit of water that's in there. I'll heat this up. Again, the key to success with this, I mean, if you want to duplicate it at home, you can. You can just heat it up over your stove at home. What you want to do is you want to make sure that you displace all of the air that's in there and replace with water vapor. And put it over here, and you can see how the can winds up collapsing. So then the question becomes, how come the one with the hot, with the water in it, why does the one with the hot water collapse while the one with the hot air does not? Oh shoot, that's hot. Sorry, shoot. Okay, that's really hot. Any ideas? Yeah.
The water vapor condenses.
Okay, exactly. And when you say that it condenses, what does that mean? You're right.
It gets cold, turns back to water, and shrinks.
Exactly. So that gaseous water in there converts back into liquid. Once it does, there's nothing left inside the can. But then we have to still account for it collapsing. What would cause the can to collapse at that point? Yeah.
You flipped it upside down, you sealed it, so there was nowhere else for it to go when it collapsed into liquid water.
Sure, but there still has to be something, though, that causes the can to collapse.
The pressure outside of the can.
Exactly, it's the pressure on the outside of the can. And I don't know if any of you have ever been to the state fair where they have the University of Minnesota physics department do some demos out there. Instead of dealing with pop cans, they take a 55-gallon steel drum and they heat up the water in the steel drum, and then they seal it up, and then they watch that thing collapse. And instead of just being a little kind of pop there, it's just a boom when the can winds up collapsing. But part of the reason why that happens is, as you mentioned, the air pressure. The air pressure is caused, or the gas pressure is caused by the collision of gas molecules. And so what I have here is a steel bar, and this is one that my uncle made me a number of years ago. And if you were to put this onto a scale, what you'd find is that this metal bar weighs 14.7 pounds. And I had to make it to some very exact specifications. And then if you look at the dimensions of this iron bar here, they measure 1 inch by 1 inch. So if this is 14.7 pounds, and this measures 1 inch by 1 inch, if I set this down on the floor, how much pressure is it exerting onto the floor? 14.7 pounds
Per square inch.
per square inch, exactly, 14.7 pounds per square inch. And now the special thing about that value is that the 14.7 pounds per square inch is actually equal to the pressure that the atmosphere is continually exerting if we were at sea level. Now, atmospheric pressure is something that will vary depending upon your elevation, because if you go up higher in elevation, there's going to be less atmosphere above you. But if we were to be able to go down to sea level, on the average, it would be exerting about 14.7 pounds per square inch on us. Here in Coon Rapids, our elevation is around 800 or 900 feet. I think it's about 900 feet. And so here on the average in Coon Rapids, that pressure is somewhere in the order of about 14.5 pounds per square inch on the average. And of course, that's something that will vary depending upon weather conditions. We have conditions of high pressure that will be a little bit larger than the 14.5. If we have conditions of low pressure, then it's going to be something less than 14.5 around here. But if you were to say, Alina, put your hand out here, and if I were to set this on here, I won't drop it all the way down. But if you start feeling this, how's that feeling? It's pretty heavy. Yeah. So I didn't even put the whole 14.7 pounds on there, but you can imagine on every square inch of your body, the 14.7 pounds, that's actually how much pressure the atmosphere is exerting on you every single second. So then that brings up the question, why the heck don't we feel that pressure if that pressure is so large? Any ideas why we don't feel it? Yeah, it's on everything. It's on every direction. So if you hold your hand out, that is not only is that pressure pushing down, but you have that same pressure pushing in the opposite direction. If you open your mouth or your nose is continually open, your nasal passages, you have that pressure exerting on the inside of your lungs, pushing out on the inner walls of your lungs at the same time that you have the air pressure pushing in. And of course, that's exactly how you wind up breathing. If you want to get air into your lungs, you increase the size of your chest cavity. If you want to exhale, you decrease the size of your chest cavity, and that causes the air to push out of there. And so the 14.7 pounds, again, is the average pressure at sea level. So if you come back to these pop cans, the reason why they collapse is because if that water condensed back down into liquid, the only place the pressure was acting on these cans was where?
On the outside.
On the outside, exactly. So you had the 14.7 pounds acting everywhere on the outside, and that causes the walls then to push in, and the cans wind up collapsing. So with that, we're going to go ahead and do some calculations here. Let's talk a little bit about gas pressure. Here we say that gas pressure is caused by collisions of gas molecules, or we could simply say molecules, collisions of molecules, with a surface. And that is such as the inner or outer walls of a container. Now if we pull out our periodic table, on the back side of the periodic table you're going to have some conversions on there. And does anybody need a fresh, clean copy of the periodic table? There you go. Michael, do you need one? Nope. That one? No. All right. So if you flip to the back side here where we have the conversions, what you'll see if you go down to the lower left is a number of conversions like this, where we have the pressures that are being provided. And in particular, if we look at these values here, 1 atm, this stands for 1 atmosphere of pressure. There's 1 atmosphere of pressure. And that 1 atmosphere of pressure, 1 atm, again, which is 1 atmosphere, is equal to the average atmospheric pressure at sea level. And the way that we measure the atmospheric pressure, I'll take you back to where I have some notes from one of my other classes. I think probably about right. Oh, where do I have those? Maybe about here. I don't know where I have them. Let's see, maybe go back one more here in the 6th. Here we go. So we use a device called a barometer, and the barometer is one that is filled with some mercury in it, and that mercury what I guess what we do is we place a glass tube It has a vacuum in the top that draws the mercury up into the column, and we measure the height of the mercury in the column. And the height to which that mercury goes in the column depends upon how much those molecules are colliding with the surface of the mercury here in that pool. And the greater the force of those collisions, the further up that mercury goes, and the less of those collisions, the less the distance that mercury goes up in the column. And we select mercury because mercury is the most dense of all the liquids. We can have such a thing as a water barometer. There is such a thing. Difference if we had a water barometer, instead of the height being about 30 inches, like this one is here, water would be drawn up about 30 feet into a column. So again, mercury is used because it's the most dense of all the liquids, and you can get a nice, easy height, at least for the early scientists and meteorologists, to measure that height inside the column. So again, we call that a barometer. And if we go back and look at some of the conversions we're going to use, if you're wondering where these heights come from, again, that comes from the height of the mercury. And these are some other conversions we would wind up using. So let's take a quick sample here of some calculations. And let's take something like 11.7, let's take a pressure of 11.7 psi. And let's convert this pressure, or express this pressure, (11.7 pounds per square inch) in units of millimeters of mercury and pascals. Let's express a pressure of 11.7 psi in units of millimeters of mercury and pascals. So we'll start with 11.7 psi here, and let's first convert to millimeters of mercury. If we convert this over to millimeters of mercury, we need to go back and look at our set of conversions. And back here we find out that 14.7 pounds per square inch, which is, we abbreviate as psi, is equal to 1 atmosphere. At the same time, 1 atmosphere is equal to 760 millimeters of mercury. So if 14.7 psi is equal to 1 atmosphere and 760 millimeters of mercury is equal to 1 atmosphere, how are these two related to each other? They're equal, exactly. So we can then use it as a conversion. We'd place the 14.7 psi in the denominator. We'll place the 760 millimeters of mercury up in the numerator. At this point, the pounds per square inch cancel out. And if we were to calculate this, we take 11.7, we'd multiply it by 760, we divide it by 14.7, and we wind up with an answer of 604.897959184. How many significant figures should this answer have? 3. So 3 significant figures would round this off to being 605 millimeters of mercury. So go ahead and do the next one here. Convert over to PA. And by the way, PA stands for 1 Pascal. 1 Pascal of pressure right here is the SI unit of pressure. So let's go ahead and do our next conversion here. Let's convert 11.7 pounds per square inch to units of pascals. And once you do that, there we go. Then answer. Hopefully you see your answer up here. All right. See if we can get our answers locked in here, please. Okay, we'll give you about 10 more seconds. We'll count down. 5, 4, 3, 2, 1. Correct answer here is 8.06 times 10 to the 4th pascals. So if we were to do this one, we start with the 11.7 psi. 11.7 psi. We're looking for an answer out here in units of pascals. And what is the conversion? What's going to go on the bottom? And what's going to go on top? How much goes on top here?
101,325.
Okay. And of course you're getting that number because we see that right here the two quantities are equal to each other. So if these two quantities are equal to each other, they may be used as a conversion. PSI is going to cancel out. You wind up getting something like 80,000 whatever, and rounding that off, I forgot that number already, was at 8.06 times 10 to the 4th pascals. Okay, so any questions on these? Okay, next up, we talk about pressure. We define pressure like this. We say that pressure is defined as being the force exerted per unit of area. So the pressure is the force exerted per unit of area. And so one of the skills we should be picking up is that when we read definitions like this, we should be able to interpret what they mean. So if you encounter the word per, what does per mean to do mathematically? What does per mean?
Divide.
Divide, right. So if we want to find the pressure, pressure is going to be equal to force divided by area. And so I have a wood block up here, and what I'm going to do with that wood block is I'm going to place it into different orientations. First orientation here is on its edge. Second orientation is here on its side. Third orientation here is lying flat. Now this is going to exert a constant force. The force is like your weight. Okay, so this has a constant weight. but I can change the pressure exerted on the table by changing its orientation. So this is orientation A, this is orientation B, this is orientation C. Which orientation of that wood block would exert the greatest pressure onto the surface? You've got the formula. Here's orientation A, here's B, here's C. Is it going to be on the edge? You should be able to figure it out based on the formula. On the edge, on its side, or lying flat. So I know there's 5 of you here, but we'll go ahead and move on. Count down, 5, 4, there we go. On the end, very good. So, next up, if we say that the force remains constant, again looking at the equation, the pressure can be increased by doing what to the area? Which obviously you must have figured out if you got the last question right. I want to make sure you're thinking along the right lines. So we'll count down on this one. 5, 4, 3, 2, 1. Okay, it's by decreasing the area, because of course, if we want to make a bigger pressure, what do we have to do to the size of the denominator here? We have to make the denominator smaller. Exactly. So we have to have a smaller area. We have to decrease the size of that denominator for it to work. So what this means then, using our vocabulary, according to this equation, we'd say that the pressure and the area are what to each other? Are they inversely proportional, directly proportional, or are they equal to each other? So we'll count down on this one. 5, 4, 3, 2, 1. Of course, that means that they are inversely proportional to each other. They're inversely proportional because, again, in order to get a larger pressure, we have to have a smaller area. As one increases, the other has to decrease. So if we doubled the area, if we made the areas twice as big, that would cut the pressure in half. Or if we cut the area in half, that means that the pressure would be twice as big. So that's an inverse proportion. Then looking at your equation. Oops. Make sure we have it here. I'm kind of going all over the place. My buttons aren't responding. All right, pressure and force. According to this equation, the pressure and the force would be. Now, we didn't demonstrate that one, but we should be able to figure that one out. Simply look at the equation. We manipulate it. Think about manipulating the force. What effect would that have on the pressure? Count down. 5, 4, 3, 2, 1. Great, that's a direct proportion. So when both of these appear in the numerator, that is a direct proportion. When one is the numerator, one is in the denominator, that would be an inverse proportion. So again, keep that in mind as we look at those. Now this is where I was going to do the liquid nitrogen demos, and unfortunately, again, I don't have that. This particular one does not require liquid nitrogen. This one I'm going to demonstrate does not require the liquid nitrogen. But this one here, I'm going to demonstrate with a syringe. And we're going to label some variables here. The variables I am going to label are P, V, and T. P, of course, is going to stand for, V will stand for, and T would stand for. Nope. Good guess, though. What other thing might we change? What do you think the liquid nitrogen would have changed? Temperature, exactly. So unfortunately we won't be able to demo that, but I think we should be able to reason it out. So we're going to give these labels here today and look at some of their effects. So we'll start by looking at this one here, and we'll say if we conduct this one at a constant T. If we're at a constant T, which is constant temperature, what I'm going to do here now with the syringe is I'm going to hold the tip here, and I'm going to press down. I'm going to increase the pressure. When I increase the pressure, watch what happens to the volume. Now I'm going to decrease the pressure by letting go. I decrease the pressure, watch what's happening to the volume. Increase the pressure, watch what happens. Decrease the pressure, watch what happens. So now that you've watched that, then answer this next question right here. Next question is, the pressure and volume of a gas are what to each other? Think what you just observed. And we'll count down. Looks like we don't need to count down. This here would be an inverse proportion. Think about this now, guys. When I increase the pressure, what happened to the size of the volume? Got smaller, exactly. And when I decreased the pressure, what happened to the volume? Bigger. It got bigger. That is an inverse proportion. Okay? So what we'd say is this. We'd put it down. We'd say that pressure and volume, P and V, are inversely proportional to each other. And if we put that into the equation, we'd write it like this. We'd say that P1 times V1 is equal to P2 times V2, where subscript of 1 stands for the initial conditions, and subscript of 2 stands for the final conditions. And so this is the way we write an inverse proportion, and this should make sense. Because if the two are equal to each other, and again, this would be initial pressure, this would be a final pressure. This would be initial volume, this would be a final volume. These two are going to remain equal. If P2 is bigger than P1, so again, if P2 is bigger than P1, that must mean, in order for them to be equal, that V2 must be, say it again, if P2 is bigger than P1, if they're going to remain equal, then V2 must be smaller than V1 in order for them to be equal to each other. And that's how we write out an inverse proportion. Okay, now the next one. I can't demonstrate, but I am sure we can reason this one out. This one would be at a constant P. And at a constant P, or constant pressure, we could talk about the relationship between the volume and temperature. And this one should make sense. So even without my liquid nitrogen, maybe you've gotten a balloon or something on your birthday before, or for an event. And we have a really cold day outside. If you take a completely filled balloon out of a party city store or whatever, and take it outside on a cold day, what's going to happen to the size of that balloon? It's going to shrink down, exactly. So if that balloon, when we take it outside, shrinks down in size, that means that the volume and temperature are what to each other? So again, think about getting a party balloon. Take it outside, the balloon shrinks. And that's outside on a cold day. That shrinks down. So we'll count down 5, 4, 3, 2, 1. All right, that is a direct proportion. Again, because if we cool it down, that means we're dropping the temperature. If we drop the temperature and that drops the volume, that is going to be a direct proportion. If we increase the temperature and it increases in size, again, that's a direct proportion. So then we'd make the statement that V and T are directly proportional. And we write a direct proportion like this. We write it as V1 over T1 is equal to V2 over T2. And again, this should make sense, because if we think of conditions, now when we write this equation, if we want these two to remain equal to each other, if V2 is twice as big as V1, so again, if V2 is twice as big as V1, in order for these to remain equal, how must T2 compare to T1? Twice as big as well. So if these are both twice as big, it'd be just like comparing 4 over 4 to 2 over 2. 4 over 4 is equal to 2 over 2 when both of these are twice the size. But this brings up a good point about the temperature, because if we talk about doubling the temperature, we need to be careful on a day something like today. I forgot the temperature coming in. I think it was about 20 Fahrenheit when I left this morning. So if you think about 20 Fahrenheit as being the temperature, if we talk about doubling that, we might think of that as being 40 degrees. But at the same time, if we looked at that temperature in Celsius, a temperature of 20 Fahrenheit is about -8 Celsius. So if we double the temperature of -8 becomes -16. And so that doesn't really make any sense. So that means we need to deal with temperatures on the Kelvin temperature scale for it to make sense. So when we talk about these temperatures in this equation, these temperatures have to be in kelvins. These temperatures here in our gas laws, they have to be absolute temperatures, and the temperatures must be in units of kelvins when we work with it in our calculations. And that's because we don't have any negative values with the Kelvin temperatures. So if we talk about doubling the temperature, we are truly doubling the temperature of whatever it is we're working with. Now, while I don't have any liquid nitrogen, I just thought about this while I was standing here. Instead of cooling it, I guess I can heat this device. So this is one now that we're going to look at. It is a constant volume device. And so we'll say if we are at a constant volume, so this one is at constant V, and it's a constant V because we have a rigid container. This here is a pressure gauge that's sitting here. I'm probably not going to be able to heat it as hot as I'd like, but you should be able to see what happens when I start heating this to the needle. I want to make sure I'm seeing it here as well. It's moving a little bit. Okay, we see it changed a bit. So now that you have this, we saw that the pressure went up as we heated it. What does that mean about the relationship between the pressure and the temperature? Again, we still see the pressure rising in here as it's very hot. Does that mean pressure and temperature, are they a direct proportion, inverse proportion, or are they equal to each other? We'll count down, 5, 4, there we go. Great, we got them all. So now, let's go ahead and write down our statements. Let's you write down the statement and the equation that shows the relationship between P and T. So write out your statement. We saw the two statements right above it. Tell how P and T are related, and then write an equation that shows P and T. equation that shows P and T. Okay, so we say that P and T are, once again, directly proportional. And if we're going to write an equation, we would say P1, where's the T1 going to go? Is it going to be P1 T1, or is it going to be P1 over T1? Right, it's going to be over T1. So P1 over T1 is equal to P2 over T2. And so this then is a way that we write out a direct proportion. And back up here where we show the pressure and the volume, this up here is a way that we show an inverse proportion. If you go through your reading, this here is referred to as Boyle's law. This one here is referred to as Charles' law. Not Charles's law, it's a French name, so it's Charles' law. And the last one here is often referred to as Gay-Lussac's law. And I'm not going to have you memorize these or anything. I just want to write them down here because if you do see some reference to them in your reading, you know what they're referring to. But I can tell you right now, I promise you 100% that you're not going to be tested on what are the names of these various laws. But what we are going to do now is we're going to take these laws. We'll take the P1 V1 equals P2 V2. We'll take the V1 over T1 is equal to V2 over T2. And we'll take the P1 over T1 is equal to P2 over T2. And now if this was our more advanced chemistry class, I would show the derivation in a little bit more detail. We're going to kind of gloss over the derivation a little bit of the equation. But now, if you look at where P is located in all cases, P is located in the numerator. If you look at where V is located in these equations, V is always in the numerator. If you look where T is located in these equations, it's always in the denominator. So what we can do, again, kind of skipping over the derivation a bit, we can rewrite this equation like this. P1 V1 over T1 is equal to P2 V2 over T2. We refer to this as being the combined gas law. This here is called the combined gas law. And that's the one that you should know. So if there's any law that you should know, this is the one you should know. And actually, if you know this law, you can derive all of the other ones. If you want the relationship between pressure and volume, that is Boyle's law, just say that T1 is equal to T2, and you have P1 V1 is equal to P2 V2. If you want to look at Charles' law, which relates volume and temperature, and say P1 and P2 are equal to each other, you have V1 over T1 is equal to V2 over T2. If you want Gay-Lussac's law, which relates pressure and temperature, we'd cover up the V's, and you'd find that P1 over T1 is equal to P2 over T2. So you can still derive all of the other independent laws from this combined gas law. And the thing to remember in this particular one is that your temperatures must be in kelvins. So your temperatures must be in units of kelvins. So with that, what we're going to do is we're going to work on a couple problems, and then I'll leave you a problem to work on and to break. And then I had planned on doing liquid nitrogen demos. I have thought of another couple demos we can do instead to move us on to the next chapter. So we'll take a break then once we do that. So let's work on these two. I have a problem for you to work on over an extended break, and then we'll move on to some new stuff. So the first one here reads, we have a sample of gas that has an initial volume of 3.95 liters, and this, by the way, is in your text. This is number 33 on page 400. So we have a sample of gas that has an initial volume of 3.95 liters at a pressure of 760 millimeters of mercury. If the volume of the gas is increased to 5.38 liters, I'd like to know what is the pressure. And we're going to assume a constant temperature. So when you work with these gas law problems, you can always start with your combined gas law, which is P1 V1 over T1 is equal to P2 V2 over T2. So we're told that the pressure is constant. So in this equation, what's going to happen to T1 and T2? They're going to go away. And what is it we're going to solve for in this calculation? What are we solving for?
Find the pressure of
Right, we're trying to find the pressure. So P2 is what we're looking for. So what I like to do with these is like to go through and label them right in the word problem itself. We're looking for P2. So that must mean that the 705 millimeters of mercury must be P1. That's the initial pressure. 3.95 liters. This must be, this is V1 or V2? V1, which means that the 5.38 liters would be V2. So now if we're solving this one for P2, we divide each side here by V2. So we divide one side by V2, and we must divide the other side by V2. Upon doing so, V2 cancels out, and we're left with P2 is equal to P1 times V1 all over V2. We substitute in our values. The P1 is a 705 millimeters of mercury. The V1 is 3.95 liters. We divide that by V2, which would be the 5.38 liters. Liters are going to cancel out. And if we take our calculators here, we'll take the 705, multiply it by 3.95, divide that by 5.38. How many significant figures should be in the answer? 3. So we'd write this as 518. The units would be millimeters of mercury, exactly. So I have this one right here, 518 millimeters of mercury. Any questions on this one? Okay, next one also comes from your text. This one comes from number 42 on page 400. For this one, we have a syringe containing 1.55 milliliters of oxygen gas that is cooled from 95.3 degrees Celsius to 0.0 degrees Celsius. We'd like to know what is the final volume of the oxygen. So of course, if we start with our combined gas law equation, P1 V1, I'll put it like this, P1 V1 over T1 is equal to P2 V2 over T2. Even though it says nothing about it here, which variable can we assume is constant? pressure, right. So we can get rid of P1 and P2 from this equation since it's presumably constant. And we're looking for, in this case, the final volume, which of course would be V2. We're looking for V2. That must mean that the 1.55 milliliters is V1. And then we have our temperatures here. The 95.3 degrees Celsius would be T1. 0.0 would be T2. Of course, what do we need to do with these temperatures? Change them to kelvins, exactly. So to change to kelvins, in case we've forgotten, on our formula sheet, kelvins can be found by adding 273.15 to our values. So we come back here and add 273.15. We add 273.15 to this one. We find out that T2 is equal to 273.15. Of course, it's really only good out to the 10th place. T1 would be equal to 368.45 out to the 10th place. So now we want to solve our equation over here for V2. To solve it for V2, we need to multiply each side by T2. If it multiplies each side by T2, T2 cancels out. And we're left with V2 is equal to V1 times T2 all over T1. We can then go ahead and substitute in our values. Substituting them in, we have V1, which is 1.55 milliliters. We have T2, which is 273.15 kelvins. And we'll divide this by 368.45 kelvins. Kelvins are going to cancel out. If we take 1.55 times 273.15 and we divide that by 368.45, we get an answer 1.14909, etc. How many significant figures are in this answer? 3. So to write our answer as 1.15. The label is going to be milliliters. Now in each of these two, you should be able to ask yourself if your answer makes sense. And so let's look and see if each of these makes sense. What happened to the temperature in this case? It drops. So what should happen to the volume? Should have decreased, and we did observe that, so that makes sense. If you wound up doing it where you found an increase, that shouldn't have made sense, so you should redo it. If we go back to this one, what happened to the volume? Did the volume increase or decrease? It increased. So if the volume increased, that must mean that the pressure would have decreased. And we see that it did decrease, and so again, that makes sense. You can always do a check on these here to see if they work. All right, which takes us to our last one. And even though this one is taken from the textbook, this is page 401, number 54, this one is actually one that is based on an experience that I had with my kids. Have you ever been to Hawaii before? Okay. I've been to the Big Island of Hawaii more than once, And the first time I went there, went to Costco. We bought one of these family packs of chips. And one of the unique things about Hawaii is that when you drive there, it's a small island. They call it the Big Island, but even the Big Island is only about, it's less than 100 miles across. You're at sea level, where the airport is, and you have Mauna Kea and Mauna Loa, which sit up at about 13,000 feet, and they have these observatories there. And so we were going to go drive to the observatory up to an elevation of about 10,000 feet. We bought the pack of chips at Costco. We started driving off to the observatory, and in about 50 miles, you climb up about 10,000 feet. And when we were going up there, we had the chips in the trunk. All of a sudden, we started hearing bang, bang, like that. And we go, what the heck's going on? And we open up the trunk, and what do you suppose those bags of chips look like? Yeah, they were all like full, and some of them had started bursting in there because of the fact that when you go up to higher elevation, you have lower pressure. The bags are sealed with the gas, and so those bags are increasing and they're exploding in the back. So, anyhow, this is one that I asked you to work on. This will take you about 5 minutes. We'll add on about a 10-minute break, and we will resume at 9:12.